Picture this. What if you could actually hold a piece of the sun? Not just its heat or its light, but the very force that keeps it burning. Imagine capturing the same energy that makes the stars shine right here on Earth within our own grasp. For nearly a century, scientists and engineers have been chasing the dream of building a tiny sun on Earth, a star we can control, giving us endless clean energy for generations to come. This isn't just some wild fantasy or a scene from a sci-fi movie. Nuclear fusion is real science, and it has the potential to completely transform our world. And now, as of June 14, 2025, we're closer than ever. A huge breakthrough at MIT has electrified the scientific community and grabbed the world's attention. The story of energy is really the story of human progress, from the first sparks of fire in ancient caves to the steam engines that powered the Industrial Revolution, to the fossil fuels that built our modern world but now threaten our future. Fossil fuels are polluting our air, heating up our planet and running out. We're stuck relying on the past to power the present, and it's putting our planet and future generations at risk. Finding a new, sustainable energy source isn't just a scientific challenge. It's something we need to survive for ourselves and for every living thing on Earth. Every star you see in the night sky, including our sun, is a giant fusion reactor, burning with incredible energy for billions of years and lighting up the universe. What if we could recreate that process here on Earth? That question has inspired generations of scientists, engineers, and dreamers. The news from MIT isn't just another headline. It could be a turning point for humanity, a moment that changes what we think is possible. A dedicated team has finally cracked a problem that stumped the world's brightest minds for decades, showing us a real path to a compact, powerful fusion device that could change everything. This isn't just about keeping the lights on or running our cities. It's about rethinking how we live with our planet and building a cleaner, brighter future for everyone. The idea of a star in a bottle isn't just a dream anymore. It's quickly becoming a real blueprint for a new era, one where we finally learn to harness the power of the stars. So, what exactly is nuclear fusion? Let's break it down and explore why it's such a big deal for our future. Atoms are the fundamental building blocks of everything in the universe, from the air we breathe to the stars in the sky. At the heart of every atom is a tiny, dense center called the nucleus, made up of protons and neutrons. Fusion happens when two light atomic nuclei, like hydrogen isotopes, collide at incredible speeds and fuse together, forming a heavier nucleus. This process unleashes a tremendous amount of energy, far more than most chemical reactions. Einstein's famous formula, E equals mc squared, explains how even a tiny bit of mass can be converted into a massive burst of energy during fusion. Unlike nuclear fission, which splits heavy atoms apart and creates radioactive waste, fusion joins light atoms together, producing much less long-lived waste. The fuel for fusion is incredibly abundant. Deuterium can be extracted from ordinary seawater, and tritium can be bred from lithium, a common element in the Earth's crust. In fact, a single glass of water contains enough deuterium to produce as much energy as burning several hundred gallons of gasoline, making fusion a potential game-changer for clean energy. But there's a catch. Atomic nuclei naturally repel each other, so to get them to fuse, we need to create conditions hotter than the core of the sun, reaching temperatures over 100 million degrees Celsius. At these extreme temperatures, matter transforms into plasma, a superheated electrically charged soup where electrons and nuclei move freely. No physical container can withstand such heat, so scientists use powerful magnetic fields to suspend and control the plasma inside a donut-shaped device called a tokamak, keeping it away from the walls. The challenge is immense. Engineers must build magnets strong and precise enough to contain the plasma long enough for fusion to occur and generate more energy than it consumes. For decades, this has been the main bottleneck, with scientists around the world working tirelessly to solve it. But now, a breakthrough in technology and materials is changing everything, bringing us closer to practical fusion energy. MIT's innovative new approach could finally make fusion a practical and reliable source of clean energy for the world. The dream of harnessing the power of the stars right here on Earth is closer than ever before, promising a future of limitless, clean energy. The next chapter in the story of energy is about to begin. Let's see how fusion could change our world forever. At MIT's Plasma Science and Fusion Center, in partnership with Commonwealth Fusion Systems, a pivotal breakthrough has been achieved. One that's not just theoretical, but a triumph of real-world engineering and innovation. The team developed a revolutionary new magnet using high-temperature superconducting tape, a cutting-edge material that can conduct electricity with zero resistance, and crucially, at much more manageable and practical temperatures than ever before. This breakthrough enabled them to construct a 20 Tesla magnet, the most powerful magnet ever built specifically for fusion energy research, setting a new benchmark in the field. Why is this so significant? Fusion power output scales with the fourth power of magnetic field strength. That means if you double the field, you don't just double the power, you get 16 times more. The impact is exponential. Their upcoming reactor, called Spark, will be about 40 times smaller than previous fusion reactor designs, yet it's engineered to produce 10 times more energy than it consumes. A dramatic leap forward. This technological leap makes fusion power not just possible, but practical and economically viable for the first time, opening the door to a new era in clean energy. The world is watching closely. This achievement could finally shift fusion from a distant, elusive dream to a real, working solution within the next decade or two. Spark's mission is to demonstrate net energy gain from fusion for the first time in human history, proving that fusion can deliver more energy than it uses. The door to commercial fusion energy is now open, and with it, the promise of a cleaner, more sustainable future for everyone. If MIT's fusion approach works at scale, it will revolutionize how we power our world. Fusion plants produce zero greenhouse gases. Their only byproduct is harmless helium. We could generate vast electricity without warming the planet or polluting the air. Fusion fuel, water and lithium, is abundant and globally accessible, reducing energy-based geopolitical tensions. A single fusion plant could power a city, operating around the clock, with a small footprint compared to solar or wind. Fusion is inherently safe. If containment fails, the reaction stops instantly, and there's no long-lived radioactive waste. Cheap, clean, limitless energy could solve water scarcity, power vertical farms, and even enable space travel. This is the foundation for a new technological revolution. The dawn of the fusion age is the dawn of a new chapter for humanity. The possibilities are staggering. The future is within reach. Fusion's rise spells trouble for the oil and gas industry, built on scarcity and finite supply. If fusion delivers cheaper, cleaner electricity, demand for fossil fuels will plummet, shaking economies dependent on oil exports. Oil giants could see their value collapse as investors pivot to the new energy frontier. Millions of jobs in oil and gas would be threatened, requiring massive retraining for a just transition. Oil won't vanish overnight. It's still vital for plastics and chemicals, but its role as an energy source will shrink. Smart companies may pivot to advanced materials and sustainable products. Survival will depend on adaptation, not resistance. The energy landscape is about to be transformed. Fusion's promise is civilization-altering. Clean air, a stable climate, and abundant energy. Fusion reactors are inherently safe. No meltdown risk and waste is manageable for centuries, not millennia. But challenges remain. The first plants will be expensive, requiring trillions in global investment. Who pays? Governments, private investors, or both? Ensuring access for all nations is crucial. Technological hurdles persist. Materials must withstand intense neutron bombardment, and fuel cycles must be perfected. The transition will take decades, running old and new systems in parallel. Overcoming these challenges demands political will, international collaboration, and relentless innovation. The path is clear, but not easy. The rewards, however, are immense. The future depends on our resolve. MIT's 20 Tesla magnet is a milestone, but commercial fusion is still ahead. The next step builds Spark, a prototype aiming for net energy gain, fusion's Wright brothers moment. If successful, Spark will pave the way for ARC, the first grid-connected fusion power plant. Even with aggressive timelines, commercial fusion likely won't arrive before the 2040s. Building these plants will require new supply chains, skilled workers, and robust regulations. This is a global effort, not a solo mission. Meanwhile, we must keep deploying solar, wind, and batteries, partners, not competitors, to fusion. The journey from lab to light switch is long, but the destination is finally in sight. The fusion era is coming. The world must be ready. Standing on the edge of a new energy era, awe and optimism are natural. Harnessing star power could free us from oil conflicts, clear our skies, and stabilize our climate. Clean, abundant energy could help solve poverty, hunger, and water scarcity. But this future isn't guaranteed. Costs are high, and global cooperation is essential. The decline of fossil fuels will bring social and economic upheaval. The path forward will require persistence, creativity, and courage. Fusion energy offers us a chance to become a stellar species, creating our own miniature suns. This is more than technology. It's a step in our cosmic evolution. The quest for fusion is about the future we choose to build. Do we cling to the past or reach for the stars? Thanks to pioneers at MIT and beyond, a future powered by the stars is now possible. The universe has shown us the way. Now, we must build it.